right, so let's continue from the previous episode last time on Quantum Mechanics 1B, Birth of the Quantum 2, Part 2. Yeah, we're waiting for the YouTube to start to the audio.
Part 2.
Sounds good. All right. All right, so we was kings. All right.
Wave aspects of electromagnetic radiation. First, consider one-dimensional waves, such as a vibrating guitar string. The string is fixed at its two ends and cannot move there.
So somebody made a note in the comment section, I think, that guitar strings don't vibrate in one dimension. They actually rotate about the axis. But I think that is linear superposition. So there's no interaction between these two modes, so that's not important, between these two directions. So what you get is a vibration, basically a rotation, which is interesting, but I'm going to ignore that for now.
In between, it can oscillate with a single bump at a certain frequency.
Okay, so this is the base frequency.
It can also oscillate with a two-bump shape at twice the single.
So two bump, twice the frequency. I'm going to assume that it's twice the frequency because he doesn't derive the equation for the frequency. So I don't know why he expects us to just accept it on faith.
Single bump frequency. Or with a three-bump shape at three times the frequency, and so on.
Mm-hmm. I'm thinking, can I derive the frequency from the... Can I derive the frequency? Is it derivable? I don't see how it's derivable. Anyway, I think in the assumption of the vibration is that the angle is shallow. So this angle is not covered. This is already something that the solution doesn't cover, as far as I know, but it's fine. Anyway, so there's three bumps, and he claims the frequency is three times the base frequency. Okay.
So on. We call each of these vibrations a mode of the string, and we index them by the number of bumps in the string.
Each of these vibrations is a mode. I don't know what he means. Like this is mode n equals 3, I guess. So there's mode 1, mode 2, and this is mode 3. Okay.
Shape. We can draw a number line and place red dots at the integers n equals 1, 2, 3, and so on.
So we can have one bump or two bumps or three or four and so on.
And each dot will then represent a mode. We use Greek letter nu.
And the frequency would just be the mode times the base frequency. Okay.
Which looks a lot like a V, to represent frequency. The frequency of the nth node is n times some fundamental frequency, nu 0. So the fifth mode oscillates with the frequency 5, nu 0.
Again, he never derived this equation. Fine.
An important question for us is this. Within a given range of frequencies, say between these blue lines, how many modes are there? For the one-dimensional case, we see that the so-called density of modes is constant. If we move the blue lines to the left or right, we'll, on average, get the same number of modes between them. We express this as Greek letter rho of nu equals a constant a.
Mm-hmm.
Now consider two-dimensional waves, such as on the surface of water or a vibrating membrane. A membrane fixed at its perimeter can vibrate with one bump at a certain frequency, or two bumps with a higher frequency. But there are two ways to have two bumps, so we can have two different modes with the same frequency.
So now, at this point, I'm confused by the N and the M. It's not clear. Maybe we can ask ChatGPT modes of vibration. What is N and M of a membrane? I wish I could copy paste easily. Like up arrow should just bring up the previous question. So this is in a membrane, elastic membrane. 2D membrane. 2D membrane. So in a 2D membrane, modes of vibration, what is N and M? Let's see if it knows. In the context of a 2D vibrating membrane, such as a drumhead, the variables N and M refer to the mode numbers that describe the different patterns of vibration on the membrane. These modes correspond to the number of nodal lines where the membrane does not move. Wow, that's already a new notion. The nodal lines. Membrane does not move in two perpendicular directions on the membrane, typically along the radial and angular. I don't know what you mean, along the radial and angular directions for circular membranes. Oh, because you could have a circular membrane or a rectangular or square membrane. So in case of a circular, yeah, you could have all different types, yeah, or along the X and Y axes for rectangular. Okay, that's our case. For a circular membrane, a drumhead, example, a drumhead, the vibration patterns of a circular membrane are described by Bessel functions. The mode, but this, we're talking about a square. This is a circular membrane, so that's a different thing. For a rectangular membrane, for rectangular membranes, the modes of vibration are described by standing wave patterns along the two perpendicular axes, X and Y directions. In this case, let me just see the audio. Notice that the audio goes down as the show continues. The show must go on. Yes. I love these. This headset is just the best. Just the best. The best investment of my life. I bought so many headsets, all garbage, garbage, garbage. And then just before I was about to invest, I was ready to invest like $1,000. I said, okay, I'm gonna go out on a limb and I'm gonna just invest thousands of dollars in a normal headset. I said, just before, let me try and buy something local. And I invested I think $30 and another couple of dollars for the courier. It took them a week, a week, a week, local week, and I got it, and it's unbelievable. For a rectangular, okay, for rectangular membrane, okay, so N refers to the number of antinodes or half wavelengths along one axis, x-axis. M refers to the number of antinodes or half wavelengths along the other axis. I don't believe it. I cannot believe it. Is it really that simple? Each combination of N and M describes a different standing wave pattern, which corresponds to a different vibration mode shapes. The fundamental mode, lowest frequency, has N equals 0 and M equals 0, meaning the entire membrane vibrates together without any nodal lines. Oh, these are the nodal lines. Higher modes over tones will have higher values of N and M, resulting in more complex patterns of nodal lines and areas of vibration. Let's see if we can find something on YouTube. You know what? Let me even quantum mechanics photons, quantum superposition explained without woo-woo. Really? I doubt it. Superposition is woo-woo. Deriving the Dirac equation. This is like the scariest channel. Richard Behiel. He has like the most advanced math that I've seen yet. This is also very advanced stuff. Microstates, okay. Stokes theorem, Green's theorem. Yeah, these are beautiful mathematical theorems. Quantum mechanics. Okay, I just want to see um, actual vibrations of a square membrane. Mm, I just want to see actual vibrations of a square membrane. I don't. Okay, let's look for it. Strictly speaking, so not every insult is an ad hominem fallacy. I don't even know if I would say that an insult is ad hominem. It's borderline because ad hominem means you're making an argument based on the person. An insult doesn't claim to make an argument. So an insult is actually not ad hominem. An insult, I would say, is just basically I would say it's a conversation ender. Like if you're insulting me, then you're no then it is apparent that you're not interested in truth. The insult is the breakdown of the discussion. That's all. So what is the purpose of a discussion? I'm not trying to convince the other side. I mean, they're welcome to be convinced. I'm trying to convince myself. I'm trying to when I debate, my purpose in a debate is to stress test my theory. I want to see how my theory or my thesis holds up against a stress test, against someone who doesn't believe it. His intuition is against mine. Whatever. I'm open. I'm open to for my thesis to be attacked. Please attack my thesis so we can find out if it's true or false. But if you are attacking me, okay, then that's not why I'm here. I'm here to stress test my thesis. If you're attacking me, then then we're not here. We didn't meet for the same purpose. So since my time is valuable, then I don't see the point of me being with you. That's all. So an insult is just a waste of time. You're just wasting my time. Now, at ad hominem, that's also, I mean, any logical fallacy is just a waste of time. Like anytime you make a logical fallacy, you're just wasting my time. I'm here to stress test my thesis. I'm here to discover if my thesis is true or false. If you're not going to help me with that, then my time is valuable. I gotta go. Maybe I'll see you, maybe I will not. But I'm not interested in wasting my time. So this is my theory of debate. The reason I debate is for me. Now, if you also are interested in finding out the truth, then you're also interested, right? Then we can meet for the same purpose, finding out the truth, whether my thesis is correct, your thesis is correct, or whatever the truth is. But if I if I realize you're not here for the same reason that I'm here. One second, we have a visitor. Sage, how are you? I can't hear you. Can you hear me? Sage. Yes, but I can't hear you. You might want to try to leave and come back. Sometimes that helps. Just mm, wait. Are you? Yes, I'm streaming. I'm streaming, talking to you right now. Anyway, so why don't you try leaving and coming back or something like that. Let me know. Let me know what's up. Anyway, let's get back to, I'll give you the link if you want to see this, the current stream. Here is the stream. This is the stream. Anyway, yeah, try now. Yes, I can hear something. Try again. Well, I heard some.
Fuck vegans.
What? I'm not a vegan. Oh, it was just a troll. Oh, they said F vegans. Oh, very, very deep conversation. You were in the vegan teachers server. Really? Okay. Cool. We were all trolling her. It was so funny. Well, I don't like trolling her. I'd like to talk to her. Ask her if she is willing to talk to me. Anyway, so let us continue. All right, so we were here. I want to see if I can find a rectangular membrane vibration. Oh, there it is. Wolfram demonstrations project, 18 seconds. So that's useless. 2 modes of vibration, square membrane.
If you look underneath it, you see there's a pulse generator here. And we've attached it to a signal generator, which is currently also
Yeah.
reached a resonant frequency here. It produces this characteristic
Don't
pattern.
care.
Hello, everybody, and welcome to another video. Today, I'd like to talk about solving the two-dimensional wave equation. If you
I don't care. I want to see. There it is. Modes of rectangular membrane. This is m equals 2, n equals 1, m equals 3, n equals 1. Good. This makes sense. So n equals 1 is basically x direction. M equals 5, m equals 6. Good. Now he's going to probably switch to n equals 2 at one point. 8. Very good. This makes perfect sense. Perfect sense. All of them are n equals 1. Amazing. Amazing. So you could have any number as long as n equals 1, and then you can do the same with n. Fantastic.
Here's the lowest frequency vibrational pattern in a circular membrane. This circular membrane is a piece of dentist rubber dam. It's stretched over a short length of PVC pipe and held in place with some rubber bands. And this lowest pattern, the entire membrane moves up and down together as one piece. Here's the third pattern.
So he's creating
membrane.
a
There are
sound
two
wave.
sections. Actually, it's kind of like a cloverleaf pattern. Two opposite sides of the membrane move up together, and the adjacent sections move down. So there's 4 regions that move alternating up and down. Here's the fourth pattern. The center of the membrane moves opposite the outside edge. In fact, there's a circle that doesn't move at all. This is a pattern where the center and the outside edge move opposite directions.
Fascinating. Absolutely fascinating.
Focusing on a
Bessel function of order 0, second root. So it's a different description. There's no m and n in this case. There is order and there is root, I guess. This is the third root. Order 0, fourth root. This is order 1, first root. Fantastic. Order 1, second root. Amazing. Order 1, third root. The number of roots, I guess, I don't know. I mean, order 1 just basically it's x and y. Order 2, first root. Okay, this is terrific. Just amazing. And here it's referenced as eigenmodes of a circular membrane, right? Eigen just means self. It's just the self. It's the frequency of the self. Amazing. So here they use circular membrane, 1 L equals 2, M equals, they have L and M, I guess. I don't see anything here. I think it's an L. L equals 3, M equals 0 mode. Okay. All right, as long as we understand the N and M.
The topic of this video is vibrating circular membrane, which is an application of multidimensional.
My God, her voice is so hot.
The topic of this.
Wait, it restarts when I hover over? It doesn't
The
continue?
topic or membrane by two-dimensional wave equation and the velocity are given. Eigenvalue modes complete by M and N has 2m nodal radii and n-1 nodal circles, excluding the boundary circle.
Amazing.
We next show an example. Set the initial displacement to be a mixture of eigenfunctions u041 and u511, and set the initial velocity to be 0. To solve for the solution u, we use initial displacement alpha to compute the coefficients a lambda by the formula in the bottom.
Okay, it doesn't matter. I mean, as long as her voice is so hot, then anything she says is correct. I hope it's a girl. It sounds like a girl. Oh, she teaches PDE. Wow, fascinating. How long ago was this? 2 years ago. Wow, she teaches PDE. I love PDE. PDE is partial differential equations. It's a phenomenal course. I love it. It's probably the most beautiful course you can take. You solve the heat equation, the wave equation, obviously, for a vibrating membrane. What else did we do? I don't remember. But each one takes basically half a semester. Let's see anything here. What about it? Uploaded. SpaceX pulls Starship from the ocean floor. Massive Flight 5 full stack test happened. Okay, I think we have enough of a notion to continue to continue watching this. Now we know what N and M mean. So that's good enough. I also wanted to check why the frequency. But here he doesn't mention the frequency, by the way. It's like it doesn't really. I don't even know if the frequency is important. Anyway, so N equals 2, but M equals 3. So 2 times 3, we should find 6 bumps. So 1, 2, 3, 4, 5, 6, which makes sense. So you see 2 basically, right? You can split it down the center. There is a center nodal line that doesn't move. But in this direction, there's 2 nodal lines. This is 1, and approximately here is the second one. It's difficult to see it from here. There it is. This is the second. This is the first. You see a straight line. So there's one nodal line and a second nodal line. So this is the 3 direction. There's 1, 2, 3. But in this direction, it's difficult to find the nodal line. I don't see it. It's hidden behind this bump. I just don't see it. Anyway, but there's one nodal line, which means there's 2. So it splits this direction into 2 bumpy areas. One nodal line splits it in 2, and 2 nodal lines split it into 3. Okay, that's the definition of the mode. The mode is both N and M. The mode is defined by N and M together. That's the mode. This is mode N equals 2, M equals 3. That's the mode.
And in general, we can have any number
Okay, now we understand.
of bumps n in one direction and any number m in the other direction.
Oh, okay. So and there he said it. So N is just one direction, M is just the other direction. Okay.
So the modes are now represented as points on a two-dimensional.
Okay, so let's look at this now. So you could have just any number, right? Because you could have you could have 0. What about 0? I don't understand. You could have 0 in all of these. You don't have to have. No, this is a bump. This is not a nodal line. So this is a contradiction to how he previously defined N and M. Because now 1 means one bump, but before 1 meant one. Oh, so 1 is the number of bumps. It's not the number of nodal lines. So here you have 2, and 1. So this is so difficult to imagine. So you have, right. So in this direction, there's only 1. In this direction, there's 2 bumps. But if you go across this direction, you're only going to encounter 1 bump. Over this line, you're going to encounter 0 bumps, but we don't care about that. So 1 means 1 bump. Okay. So you could have 1 bump in one direction and 1 in the other, 2 in the other, 3 in the other, right? We saw a video where we had 1 bump in one direction and we even saw 10 bumps in the other direction. And you could have 8 and 8, or obviously this is just perfectly symmetrical, so it's the same as that one. So in any combination. Perfect.
as points on a two-dimensional grid indexed by two numbers, n and m. The corresponding frequency is a fundamental frequency, nu0, times the
Okay, so there's some fundamental frequency of 1 and 1. So this is the fundamental frequency, and apparently this is the frequency of any other combination of n and m. Fascinating. This looks like Pythagoras's relationship. Strange. Pythagoras keeps coming up.
square root of n squared plus m squared. This is constant on a circle, so a range of frequencies corresponds to the area between two circles. At higher frequencies,
Let's see. So the frequency is n squared plus m squared. So all of these have the same frequency. So this is 2 and 1, right? This is 2 squared plus 1 squared, or 2 squared plus 1 squared. But this is 2 squared plus 2 squared. How could you say that this is the same frequency? I don't understand. You could say that this one and this one obviously have the same frequency. Wait, what is he trying to say?
fundamental frequency, nu0, times the square root of n squared plus m squared. This is constant on a circle, so a range of frequencies corresponds to the area between two circles.
A range of frequencies. Course, I don't understand. What is he trying to say? I don't know. Like before, we said that the number of bumps is going to be a constant in any range. What is he trying to say here? I don't get it. I don't know what he's trying to say. N squared plus m squared is a circle. If you look, if this is the real number line, this is the real number line, then this is 2 squared plus 0, and this is 0 plus 2 squared, and this is whatever number it is 1 point something squared plus 1 point something squared. It also gives 2 squared. So all of these give a certain frequency. So this is a certain frequency, which is, this doesn't exist. This is 2 and 0. There's no such thing as 2 and 0. I don't know what he's trying to say.
At higher frequencies, there will be more area, hence more modes for a given frequency range.
Okay. At higher frequency, there's just more modes. Sure. At a higher frequency, you have more modes. At a lower frequency, there's less modes. Because the modes, I think, are n times m. There's n times m modes. Or something like that, right? Is it n times m or n times m over 2? Because of symmetry. So you could argue that you should cut it in half. But I think it's n times m over 2, or n times m minus 1 over 2, or n times m over 2 minus 1 or something.
So here there will be
Because, or maybe plus 1, I don't know. So this is nu equals 8, nu naught. Well, it's right outside. What is he trying to say now?
more modes with frequencies between 7 and 8 nu0 than between 2 and 3 nu0. For two-dimensional waves, the density of modes is proportional to frequency. And we
The density of modes is proportional to frequency. So this line is the line of a frequency, right? Because this is the definition. Well, we'll take this for granted, that this is the equation for the frequency based on the mode. So this is a line of a constant frequency. This is a line of a constant frequency. So between these two frequencies, there's only these three modes. Between these two frequencies, there is 1, 2, 3, 4, 5, 6, 7, 8, maybe 9 modes. So we went from 2 to 3 to 7 to 8. So he says it's linearly proportional. Why? Again, he doesn't derive equations. So he's not going to derive equations in this course. I don't understand how you can teach if you're not deriving. What's the point of teaching if you're not going to derive the equations? You can derive them quickly. This is a video. Just derive them quickly. Like, show it quickly. You don't have to teach it again and again and again. Just show it once quickly. You're going to show an equation. Show how you derived it. Why is it so difficult? Why do I need to guess each derivation? Yeah. Let me just okay. Yeah. Terrible. This is no way to learn anything. You can't learn with assertions. Anyway, Rho knew the density of nodes or modes. Modes means eigenmodes, self vibration. The system enters into a sustained vibration state. So the density for a certain rho nu, so rho at nu is equal to a times nu, some constant times nu. So what he's saying is this range, as this grows linearly, the area here, basically you could argue that the area here grows linearly. So all we need to prove is that the area under this circle, or between these two circles, has a linear relationship. So it's not r squared, but it's r. So this area, right? So this is, I don't see it because this is 2 pi, this is pi r squared. The area in a circle is pi r squared. And this is pi, so this is pi r squared minus pi r squared. But this is these two r's. That's the area here. So it's some delta. So it's pi delta r squared, basically. But the delta r is the same. This delta, right? It's pi r squared, but it's just delta r. That's the area here. So, but the area here must be smaller. This is pi times delta r, but if it's the same delta r, no, it's not delta r. It's not. It's pi r squared minus pi. It's pi. Okay, pi. Everything has pi, so we can ignore pi. So this is 3 squared minus 2 squared. This is this area. we're ignoring pi because this also has pi. And this is 8 squared minus 7 squared. So 8 minus 7, let's go from 2 to 3 to 3 to 4. So 3 squared minus 2 squared, what's the proportion to 4 squared minus 3 squared? So it's basically 4 squared minus 3 squared minus 3 squared minus 2 squared. So the 3 squared, right? So this is 4 minus 3 minus 3 minus 2. So 4 squared. But what I'm trying to say is that we have 4 minus 3 minus, right? We want to see the difference. This, basically 4 minus 3. I'm just trying to derive this equation because he doesn't show it. Let's see if ChatGPT knows how to derive it. So rho nu equals A nu. Okay, let's try it. So rho nu equals A nu. Rho of nu equals A nu. Let's see if ChatGPT recognizes this. The expression represents a simple relationship where the quantity rho nu is proportional to the frequency, A being constant proportional spectral density, Planck's law simplified. This is exactly our discussion. In some contexts, rho of nu can represent the spectral energy density exactly, or the distribution of energy as a function of frequency nu, often used in relation. Okay, the expression might be simplified version approximation in a specific regime, low energy approximation. However, this linear dependence density of states also true. Yeah. Can you? Okay, I just want you to derive it. Can you derive it? So this is 2D. 1 second. 2D membrane vibration. Please derive this. You realize that it's doing this in real time. It's auto-completing in real time. But why is it, so it says here that nu equals nu over 2 pi k. N of k area of circle in k space, pi k squared. Convert k space to frequency space. Well, at least we see the proof. This is nu and this is v. The wave speed. That's not what I want. What I want, I just want to prove that a strip of a circle grows linearly as the circle grows. As the circle grows linearly, the area between two consecutive circles. Let's talk about integral circles. Oh my god, I need to do this. I have no choice. I have to do this here. Come on. Did I do this? Looks like my handwriting. I don't recognize it. Ether base. Didn't I do this yesterday? Okay, we can continue here. Okay. So what I'm saying is that, right, we have r2 squared, right? It's pi r squared minus, or not 2, but this is some n, and this is n minus 1, where n is an integer. So this is the area that, right, it's pi r squared. So this is pi times this minus the smaller circle. So this is going to be n minus 1 minus n minus 2. So this is 4 squared minus 3 squared minus 3 squared minus 2 squared. So, right, you can see right away that this and this cancel out. And then you end up having plus this. So the difference between two consecutive circles, it's all times pi. But the difference is, this is basically 4 squared plus 2 squared. I don't see the area growing linearly. But maybe it does. Yeah, I think it does. I think the way to prove it, I think I have a different proof, a simpler proof. So you take a circle and you grow the circle. The question is, by how much, right? But imagine we're talking about the actual width. The actual width of the circle. The circle is not a line. It has a width. This is the 4 minus the 3, or this is the 3 minus 2, and this is 4 minus 3. So we're saying that the width is the same. The question is, what is the area compared to this area? We know the difference R. We know R1. So we know this is R1 and this is R2. It's not squared, it's just R1 and R2. So given R1 and R2, and given that their width is the same, what is the area of R1? What is given a ratio R2 to R1, what is then the ratio of area 2 to area 1? where the area is the red itself. How much paint do I need to use to paint R1 compared to R2? So R2 and R1 are given. Let's say it's a linear growth. How does A2 to A1 compare? So we know that area, this is not pi r squared. This is 2 pi r times the width. So the width is constant, so it's just 2 pi r. So it's just r. That's why it's linear. Because the area of this circle that we're talking about, the amount of paint you need, the amount of red paint you need for this job, it's a relation, it's correlated to 2 pi r. So this is R2, and this is going to be R1. And we're going to ignore the 2 pi because it's going to cancel out. So this is not R squared. This is the ratio of R2 to R1. So given the ratio of R2 to R1, the area it's going to be linearly proportional. That's the answer. Okay. That's the proof. My God. It's going to be so difficult to go through this course. Let me see what else we wanted to do today. Let me see my schedule for today. Oh, come on. Oh my God. Yeah, I need to take care of one more thing. Yeah. Okay, software update. Okay, that's good. Anyway, so okay, so that's the answer. So the density of modes is proportional to the modes. So this density or this area grows linearly. That's good.
We write rho of nu equals A times nu. Finally, we get to three-dimensional waves, such as the oscillations inside a microwave oven. These are a bit harder to illustrate. The bumps now correspond to cubicles inside a larger volume. We could, for example, divide the volume into 2 regions in 1 dimension, 3 regions in a second, and 4 in the third. So our modes are now indexed by 3 numbers, n, m, and l. Each mode is a point in a 3-dimensional grid.
Now everything is so much simpler now that we've seen other videos where they show, where they explained n and m. Now he's adding l. So we have n, m, and l. Now everything is much, much simpler. He could have explained it slower, but he chose to skip steps. And we paid the price, but that's fine. It's all par for the course. Cheseco. Of course, I didn't get the notification when he said hi. Of course, because getting notifications is like, who needs that? Who needs notifications? That's like, can I talk to StreamYard? Can I ask them for a notification? Is it too much having issues? Can I click on having issues? What would happen if I would click on having issues? Would it destroy my stream? Is there a copy? No, there's no copy. Okay, whatever. Let's continue. Okay, I did want to. I want to see 3D vibrations. Wow, who is she? Jesus. Sylvia Picozzi, spin orbit coupling, a small interaction leading to rich physics, materials cloud. Wow, she's beautiful.
Pleasure to chair this Marvel distinguished lecture. And our guest today is Silvia Picozzi from Italy. So I will give just a
Italian chicks are awesome.
very short introduction.
And we basically do density functional theory, but we benefit a lot from symmetry and
Oh my god. Oh my god. Jesus.
Symmetry analysis.
Oh my god. Yeah, wait, I can't hear it.
to understand the physics. So what we really like is to explore the microscopic mechanism underlying the effects that we see. So after, of course, we understand the mechanism, then we try to optimize the.
Very nice, very nice. Okay, what else we got? I cannot believe people think. I
Oh,
don't know what that is. I don't know what that is. Elon Musk moving all of his
Social
X to Texas 54 minutes ago. Ellie in space. She's
social
hot.
media site
She's hot.
social media site X is now officially headquartered in Bastrop. 1 week ago, CEO Elon Musk said X's San Francisco headquarters was permanently closed. No word yet on how many jobs this move could bring to Central Texas.
So part of the reason I'm making this video is because X headquarters closed down in San Francisco and are actually moving here to Bastrop, Texas, not exactly in Austin. And if you guys vividly remember, in May of 2023, at the lithium refinery groundbreaking, I asked Governor Abbott if he would want Twitter or X to be moved here.
It's nice to meet you, Governor Abbott. Elon's moved a lot of his industries here. Do you want to see him move Twitter here?
We don't have time for any questions. We would love for Twitter to be here in the great state of Texas. Elon loves doing business in Texas. We will continue to keep Texas the best state to do business, including as the location of Twitter.
What do you think of the truck?
It's fabulous.
You heard it from the man himself. He would love to have it.
if you're like me,
What else we got? Why are Americans siding with Hezbollah? Deadliest fighting.
Hi,
in
friends.
decades.
Welcome back. So I want to give you an update what's going on in the markets today.
Let me guess, he's anti-Israel.
Hi, friends. Welcome back. So I want to give you an update what's going on in the markets today and also, too, what's going on around the world. And unfortunately, we have to talk about the fighting in the Middle East. Unfortunately, because it just keeps getting worse and we're worried about full-scale war. I've been following the last couple.
No, it's not getting worse. It's getting better. It's called surgery. And, you know, when you get surgery, you're getting better. When you're cutting away your cancer, you're getting better with every cut. It doesn't look good. It looks terrible. There's blood everywhere, but you're actually you're getting better. So things are getting better. Things are getting better with every passing second. So if I can help you with that, let me know.
Been following the last couple of days. Israel had the whole pager explosion thing, and then Lebanon was firing missiles at Israel. Now Israel's conducting airstrikes.
Lebanon is not doing anything. It's the Hezbollah which is firing rockets at Israel, which it has been doing since October 8th or 7th last year, whatever. So it's been basically daily rockets and attacks from the Lebanese side, which is Hezbollah, So nothing has changed. It's now that Israel finally, after a year of being attacked, is finally reacting. Finally.
Conducting airstrikes. The fighting is getting worse.
No, the fighting is not getting worse. The Lebanese or the Lebanese side is calming down because Israel is taking out their facilities that have been used to attack Israel. So things are calming down.
Conducting airstrikes. The fighting is getting worse. Israel has issued a warning to civilians, basically evacuate. So it means that we're preparing for a large scale fighting. Whether or not this becomes like all out war, that's sort of the biggest fear, of course. But I mean, already we saw this.
No, it's not the biggest fear. It's the best thing. I mean, I'm the last person to be pro-war, but when you have an aggressor that is not relenting, then you have to go to an all-out war, destroy them, and have peace. Yeah, you know, if you live next door to a criminal that keeps attacking you, and with every passing day, these attacks are getting worse and worse. You know, nothing is going to change until you go next door, you bash their face in. Maybe you need to take them out, and then you have peace. And then you can start your life.
Saw the situation in Gaza and this.
Anyway, yeah, this guy's an idiot. He hates Musk. He probably hates Trump. He's an idiot. Nothing to do with reality. Completely detached from reality. Anyway. I don't want to get bogged down with too many reactions. I just want to find a 3D vibration animation. Let's see. That's good. So but this is the molecular vibration, and I just want to see basically a 3D membrane, but there's no 3D membrane that can vibrate. Nothing.
Used to increase the temperature.
This is temperature. I don't know what this is. That's not 3D.
Good, hello, welcome to Onion Skin. In this video I have a simple tutorial for you, and towards the beginning of the
Water turning to
in and out.
So there is no 3D vibration animation.
Fix one end of by the geodesic effect would relate only to the we fill
Johnson, that's kind of cool.
tie one end of a rope to a window.
This is a random vibration, 2-second animation.
क्या आपने कभी इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम के बारे में सुना है? हो सकता है नहीं सुना हो, लेकिन इससे रिलेटेड
This is actually a good animation.
क्या आपने कभी इलेक्ट्रोमैग्नेटिक
That's actually very good. That's how electromagnetic waves are generated. So you have a charge that's moving up and down, but the magnetic field is moving clockwise and counterclockwise.
क्या आपने कभी इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम के बारे में सुना? यही चार्ज जब एक्सेलरेट होने लगे या ओसिलेट होने लगे तो इससे प्रोड्यूस होने वाला मैग्नेटिक फील्ड चेंज होने लगता है और ये मैग्नेटिक फील्ड इलेक्ट्रिक फील्ड को अफेक्ट करता है जिससे इलेक्ट्रिक फील्ड भी चेंज होता है।
Amazing.
इलेक्ट्रिक वैसे लाइट की स्पीड को इमेजिन कर जैसा
Right.
कि हम जानते हैं स्टैटिक चार्ज
No,
इलेक्ट्रिक फील्ड प्रोड्यूस
that
करते
is
हैं।
not static charge. That's incorrect. Static charge.
लेकिन जब वो मूव करते हैं
Static charge doesn't flow. It stabilizes. It doesn't. It's not continuous. It changes the space and then it stabilizes, and it never changes again.
लेकिन जब वो मूव करते हैं तब इलेक्ट्रिक फील्ड के साथ साथ मैग्नेटिक फील्ड भी प्रोड्यूस होता है। यही चार्ज जब एक्सेलरेट
Yeah, the magnetic field doesn't move. Anyway, I don't want to get bogged down to all these. These are great animations. One second, let me see what I got. I heard an incoming message, but I don't think it's relevant. No, it's not important.
Is performed at the injury site. This energy penetrates the injured tissue and causes an analgesic effect. By intense local stimulation.
Okay, so no one has done a 3D animation. This is 2D. So there's no 3D vibration mode. She's not so hot. She has a lower, it's called an underbite, I think, or an overbite, or an underbite, I don't know. 3D vibration, yeah, there's nothing. I don't see anything. No. You would expect to see a lot of these things. Why can't you find any 3D vibration? 31 million views. Look at this 3D hologram. You could have these 3D. It's not real. I don't know if it's 3D because from our direction it looks. It's not 3D. This is incorrect. This is not 3D. Cochlear animation. Everyone I've reviewed does not understand it correctly. Okay, there's nothing. There is nothing. Okay, so we can give up on this. Let's just go back to his. Let's see what he says.
And a given frequency.
So he doesn't show, he just showed the nodal planes, which is fine. So there's N, L, or N, M, and L, which is fine. So it's the same story. This time it's two strips. It's two volumes. How do they compare? So can we predict it? Let's try and predict it ourselves. So this time we're going to have two volumes. So there's going to be two volumes. So again, it's the same story. So one volume, that's not a sphere. So we have one sphere, one shell, and another shell. But this time we're curious about the volume of each shell, given that it's the same thickness shell. So imagine an egg. This is a small egg and a bigger egg, but the shell thickness is the same. So again, given R1 versus R2, what is V1 versus V2? So this time let's put it R sub 1 versus R sub 2, the small, this is 1 and this is 2. So how does V1 compare to V2? So V1 is like 4/3. We don't want the volume. What we want is the area, because we're going to multiply it by the thickness, and the thickness is the same, so it drops out. So it's just the area of the surface of a sphere. So what is the area of a sphere? So let's ask ChatGPT, what is the area of a sphere? You're giving feedback on a new version of ChatGPT. Which response do you prefer? 1 second, let's go to control 0, so it's the same size. So which response do you prefer? Responses may take a moment to load. Response 1 is this, with an example and explanation. So they're the same. It's interesting how much I like bullets. Bullets are much better. So the area of a sphere is pi r squared. This is my preference. Okay. Anyway, it's 4 pi r squared. Okay. It's 4 pi times r squared. Okay, we can close this. We were here. So it's 4 pi r1 in this case squared, and again this is going to be r2 squared, and the 4 pi drops, no, the 4, I wanted to go to yellow, the 4 pi drops out. So the ratio given r1 r2, the volumes are r squared, or the square, the ratio is the square. So it's relative to the square of the radius. So it grows as the square of the radius grows. The volume grows relative to the square of the radius. Okay. Which means that the equation is going to be rho nu, because this is the new space, it's LMN, is going to be some constant, obviously, times the square of nu. That's what I think.
T represents a spherical surface. The density of modes now corresponds to the number of grid points between two spheres. This is proportional to the square of frequency, and we write rho of
Got it. Okay, so I'm beginning to understand. He claims that the frequency that's the equation of the frequency. Yeah, I'm assuming. I assumed. So I assumed his diagram. So this is just a sphere. NML all squared just describes a sphere. So the frequency space is this sphere. This is the relationship. Why do I care? Why do I care that this is the frequency? That the frequency does this describe what we just saw? Would I have been able to predict this? I don't know. We never derived this equation. But the frequency, that this is the frequency. Let's try and ask ChatGPT to derive this equation. So please derive rho of nu equals nu naught. I don't know, nu 0 times the square root this is square, is the square root square root of n squared plus m squared for a 2D vibrating membrane. Please derive the density of frequency, the frequency density. Please derive the frequency density. Okay. I should have said frequency density, but it probably knows. In this context, there it is. Yeah. Refers to the frequency of vibration for a mode of a 2D vibrating membrane. Step-by-step derivation. Yeah. So you start from the wave equation. This is the differential. This is the partial differential equation in 2D. Fascinating. So it's expressed as the second. This is the second del, which is basically the second derivative. Wait a minute. Why do you say this? This is x, y, and t, but you already have over t. The second del of phi. I don't get it. This is very interesting because I I took PDE like a million years ago. I don't remember anything, but this makes sense that it's some, we're assuming some form of a solution. Anyway, what is del squared? Is the 2D Laplacian operator which acts on the spatial coordinate x and y. So it's only x and y? Why is it only x and y? Why not t? Okay, but if you say it's only x and y, then fine. Then this is just the second derivative over x and y, which is just a wave equation. This is just a wave equation. It's fine. But even this, you're assuming, how do you know that there's a v squared here? How did you derive this equation? But okay, let's assume this equation. I saw a derivation the other day. Anyway, so you're assuming, okay, we'll come back to derive this equation, but assuming this equation, so the solution is to assume this form of a solution, some sort of a separation of variables. That there is a function x of x, y of y, and t of t, and they're multiplied by each other. And that's the form of the wave equation. That's fine. By substituting this, so you actually, you see that whatever, that the second differential with respect to x is this. By substituting this in the wave equation, separating variables, we get the following two spatial equations for x and y. Okay. And then obviously this is x and this is y. Fantastic. Now you have here n and m. Here is the introduction of n and m. That's good. Length of the membrane. This is just the length. Okay, that's fine. Frequency. This is the frequency. That's the answer. Almost. This is just kx squared. This is not yet n squared plus m squared, right? So it's not the final form. We're looking to prove the density of frequency density. So this is just the frequency. Okay, so that's the frequency. And you're gonna define using the expression for kx is this. Simplifying, we get this. This is the fundamental frequency. It's this. That's the frequency of any vibration mode. But this is the base frequency. So we don't care about the base frequency, what it is. All we care is that we proved that any frequency is this function. So we proved that this is the frequency space. So the frequency density comes out of that. Let me see, I have a message. What's the message? Notification. Check out your analytics. Your weekly recap is ready. Okay, I'll take a look at it later. Let's see what we got. Oh, we have more comments in the comment section. So RKI says, why are you using this AI? Why don't you use ChemAI or something like TutorMe? Oh, I don't know anything about that. Use Chemistry Chem by clicking on Explore GPT. Okay. it's confusing here. This is confusing. It's really straightforward. I don't see the. I'm able to follow, and I'm a complete dummy dum dum. Like I don't know anything. I'm very happy with the current state. I mean, we've gotten this far. Let me just make sure everything is okay. So at this point, I'm satisfied. We have the space, the density. Oh, sorry, not the density. We have the space of the frequency. This is just a frequency space, which this is a 2D frequency space. But we didn't prove the frequency density. The frequency space is fine, but we were looking for the. I asked ChatGPT for a 2D, please derive the frequency density. In this context, the frequency density refers to the frequency of vibration for a mode of a 2D vibrating membrane, such as a rectangular drum head. Here, N and M are integers that describe the mode numbers along two perpendicular axes, such as X and Y. And nu naught is a constant related to the physical properties of the membrane, such as its tension and size, step by step. So they didn't completely derive this. We could ask it to derive that, but we can also ask it to derive this. So the vibration of a 2D membrane is governed by the wave equation. So can I paste this here? Can you derive that? Oh, I didn't ask it to derive it. The equation you are referring to is a 2D wave equation for a vibrating membrane. It describes how a function psi of xyt, which represents the displacement of the membrane at point xy, and time t evolves over time. The correct form of the equation is this. Del squared is the Laplacian operator in 2 dimensions, which applies to the spatial coordinates x and y. V is the wave speed on the membrane, and partial squared of psi is the second partial derivative of psi with respect to time t. Psi represents the displacement of the membrane at time t in position xy. Breaking it down, Laplacian operator, del squared in 2D, Laplacian in 2 dimensions, is given by, so this is the Laplacian. It's just the second derivative over x plus the second partial derivative of psi to y. This term describes how the displacement changes spatially across the membrane. This is a snapshot in time, but it didn't derive it yet. Wave equation. Now this is the wave equation after we expanded the del squared operator. This is a second order partial, but yeah. You didn't derive it. I wanted you to derive it. Okay, I'm not gonna do that now. That's like not for now. It's fine. Let's stop it. It's fine. It's fine. Thank you. Okay, so we was here, so everything is fine now. So we're kind of happy with this. We still need to derive the wave equation itself, which is fine. I mean, there is, if you want to see a good derivation of that equation, Stern and Gerlach experiment. Okay, so what I want to see is the 2D wave equation derivation. Yeah, this guy.
The partial differential equation for the system right now, but it will definitely come into play when we actually try to solve this and apply some boundary conditions. So let's consider I've got two small kids and a dog in the house. So when somebody finds this mess in the morning, I'm just going to blame it on them. But anyway, I think that sets the stage here of what we'd like to do.
This is the drum.
Let me see that direction here. Membrane is fixed in kilograms per
So anyway,
y,
yeah.
and at any temporal.
So this is the differential or the infinitesimal surface that he's going to analyze now.
Coordinate time t. So that's the along the boundary.
So he's making assumptions. That's fine.
This is not like a single string where, yeah, there's definitely a clear single value of tension throughout the string, right? This is now a membrane where the tension is spread out over the entire surface. So to make the units and the math a little bit easier, let's just conceptualize tension as force per unit length here. And we're going to say that it's the same everywhere and it doesn't change. Even if the membrane is vibrating up and down here, it's going to basically be the same tension everywhere. Okay, and finally, assumption number 5 here is that out of plane deflections are small. Large membrane, so like, in this case, it was our big dish towel here. But what I would like to consider, okay, now, what might be helpful is let's draw a larger version of this picture here, and we'll do this in 3 dimensions here. So let me just draw a 3-dimensional coordinate system first here. So here's X, Y, and then Z, which is actually our deflection, right? Out of the plane here. So what I'd like to do is I want to cut this little chunk of surface out here from this top view and place it in this 3-dimensional view. You know what actually might be helpful? Let's actually physically cut out this dA out of our membrane, right? This thing's already a goner here because I think I already drawn it with a Sharpie. So I think I'm gonna get in trouble anyway. So if you're gonna get in trouble, let's just go the whole 9 yard, the whole distance table or something. But I guess it might make it a little hard to use scissors here. I do need an assistant. I should get my little daughter this kind of stuff. All right, here we go. A rough picture of what this thing looks like, right? So let me grab it. All right. So here's this projection in the XY plane here, right? The left side of it again we said was, whoops, actually that should not go like that. That should go like the Y here, right? And now these points can get projected up to where the surface is actually located. Okay, something like that I think is a halfway reasonable drawing of this membrane here, right? Okay, so now what I'd like to consider here is let's consider what kind of forces are acting on this membrane here. So along this front face here, right, that we've cut out, there's going to be some force that if we look at sort of the average value here where this is angled here, you're going to have some force like this coming off of this face, and the magnitude of that force here, right, is this going to be something like the T times the distance, right? So that'll give us the units of newtons or units of force. So it's basically the tension times the distance or the length of this edge here, right? And we see that the length of that edge is just delta x. So this force here is T times delta x. Similarly, on the back side, you're going to have another similar T times delta x, but it's going to be oriented and pointed in a slightly different direction because, right, we're taking this funny membrane here, and this thing is laid out and it's draped over in a surface. So the front face and the back face and the left side and the right side, they're all pointing in sort of different directions. And furthermore, the slope of that pointing changes as x and y change all over the face here, right? So we'll investigate that again in a second. But okay, so we get up these on the front and the back face. Similarly, on the left and the right side, we also have forces acting on this of T times delta y in this case, and also T times delta y. Right. Okay. So it actually might behoove us now to look at a planar view here. Let's just look at this in the XZ plane. So let's draw that a little more cleanly down here. So if I draw this like such, here you got X and Z, which is really our deflection, U of X, Y, right? So in this case, again, let's use the same color here. You got your membrane here, like such here, and T times delta Y, right? And over here you got T times delta Y here, right? And again, this picture is slightly misleading again here, right? I've drawn it like it's sort of making the assumption that, again, here's our little area, delta X, delta Y. We're now looking at it directly kind of on an edge here. And the way that picture is drawn, it's basically, it's misleading in the sense that I don't think I can get the camera angle right. It's something, geez, yeah, I can't. It's something like this here in that picture where it makes it look like there's no variation in the surface as Y moves, as you go in and out of the board. But one of these edges, maybe that back edge is tipped up quite a bit. So you definitely can see that there's some variation in slope as you move in the Y direction here. But what we're drawing here on this board here is let's consider this to be sort of the average angle here of this membrane as you move along that direction. So in other words, what I'm going to assume here is let's call this angle here alpha. And that is this average angle here of where this average aggregate tensional force on that edge acts. Similarly, on the other side, we can do the similar thing here. Let's call this angle here beta for that average angle. Okay, great. So with this, I think we're pretty good to go here. Let's go think about how can we go ahead and derive now some equations of motion based on this system, right? We have effectively a free body diagram of our system.
He's ignoring the thickness, which is fine because it's a constant. And he defined the tension per unit length, not per unit surface, which is fine.
System. So let's just go ahead and apply Newton to this. So first thing is let's consider this thing in a horizontal direction, right? So let's look at horizontal forces, right? Well, I guess what's a better notation for this? Because this is all sort of horizontal. Thing like what? It's T delta Y times cosine of beta, right? Minus T delta Y cosine of alpha here, right? And due to our small angle approximation, right? We said that, all right, these small angles are basically 1 here. So we end up with 0 here, right? So this is great. What this shows us here is there's no horizontal forces in this situation due to our assumptions, which basically means, right, no horizontal motion. So the only motion this membrane is going to
experience. Right. Obviously, we're assuming, we might as well have assumed there's no horizontal motion. Because it's small angles, it's fine.
Is in the vertical or the out of plane direction. So let's look at that right now. How about vertical forces? right? So in the vertical forces, right, we can also do a similar thing. Some of the forces in the vertical, right, sine beta is here. And now let's go ahead and use our small angle again approximation, right? Which basically said if you had, sine of some small angle, let's call it theta here, right? Didn't we say that's effectively theta here? Or the more useful way to look at this is effectively tangent of theta here, right? Those are all the same thing because tangent here, right? So what we end up with here is some of the forces in the vertical, right?
So this is now the vertical. So the vertical is T delta Y times, well, it's this one, times sine of beta is the vertical component, and the same goes for sine of alpha. Okay. But he says that because of small angle, sine theta is equal to theta is equal to tangent of theta. And I think he's going to want to plug in tangent of theta.
We could just write this thing as T delta Y times the quantity tangent beta minus tangent alpha. Right? Okay, let's look at what are tangent alpha or tangent beta and tangent alpha. Let's look at tangent beta here, right? Tangent beta is if you come back over to this.
Now you can go back to his lecture on a 1D wave, and he did very similar things. So if you want to listen to it like in a different perspective.
This picture, tangent is opposite over adjacent here, right? So it's almost like rise over run here, which is effectively the physical slope of this system here at the right.
Very good. Rise over run. The tangent is is dy dx. This is fantastic.
Edge in this case. Correct. So what we see here is basically tangent beta is the same thing as partial u with respect to x at this location. So maybe we should write that down here. Let's write this real quick here. So we can say that tangent beta here, right, is basically partial.
Sorry, it's not dy dx. No, not dy dx. This is du dx because y we have x, y, and u. U is the wave equation.
U with respect to x evaluated at x is equal to x plus delta x here, right? And at some y value of, again, we gotta be a little bit careful here. Well, actually, no, we don't have to be careful, but I like to be kind of cautious about this here. So this is at some, again, the y location, this can change here, right? So what we want to note here is let's just pick some y1 value, which is in between y and y plus delta y here, right? Because again, all we're trying to do here is basically say that over here, this was tangent of this sort of average aggregate angle beta here, right? Well, I want to equate that to the physical slope here. But again, we talked about earlier, the physical slope of this thing in the x direction is
Okay, I mean, you could just assume it's infinitesimal. You could assume that y doesn't change, no? I don't know.
changing as y goes in and out of the board, right? So I'm just going to pick some value y such that the right-hand side equals the left-hand side. Again, it's, if you want to just boil this down and reduce, it's just like we're looking at averages here, okay? Okay, so that's great. We can do the exact same analysis for alpha here, right? This is du dx. So again, tangent alpha, if I look at this picture, it is opposite over adjacent on this side, or rise over run on this side, or physical slope of u with respect to x here at the left side of the piece of membrane here, right? So this is du dx evaluated at x, and at y equals some other y2 value. How about between y and y plus delta y, right? Okay, what's alternate notation for both of these? We can also say that this here, you can also write this as ux here at x plus delta x and at y1, right? And similarly, this thing is, the shorthand notation will be ux at x and y2, right? Awesome. So let's substitute those in for this expression over here.
Okay, let's look at this 1 second.
And what do we get here? So we get...
Okay. So tan beta, tan beta is du dx. So it's rise over run. This is dx and this is du. So it's du dx, which is u sub x at x is the value x plus delta x, and y is y1. I'm assuming this is 0.1, and this is going to be y2. Because he's going to do this minus that. It's beta minus alpha or something. Z is equal to u. Okay. U is a function of x and y. This is a snapshot in time. So tan alpha, for similar reasons, is just over x. Okay.
Oh, and actually, sorry, vertical. Maybe we should have said this is some of the vertical on the left and right side, right? Because we actually haven't dealt with the front and back. We're gonna do that in just a second here. So really, we
right. We need to analyze this, but also then we need to do the same for y.
Tension delta y times ux of where was it? Yeah, here, x plus delta x and
so tension,
y1, right?
Tension delta y and sine beta becomes tan beta, and tan beta becomes u sub x at x plus delta x y1.
Right, minus ux at x and y2.
Minus ux at
Right?
x at
Okay,
y2.
great. This was some of the
okay?
so some of the forces in a vertical
Yes.
on the left and right side. Okay,
Yes.
you can do the exact same analysis for the front and the back face of this object here, right? Of this small dA, and you would get virtually the identical expression here. So let's just write that
You're
down.
going to get a mirror image of this. So left and right becomes front and back, and wherever you have x, I guess, will become y. Wherever you have x becomes y, and y becomes x for symmetric reasons.
What you would end up with? You'd end up with some of the forces in the vertical on the front and back faces here. It's going to be tension delta x here, and now you would end up with uy at, again, some average value like x1 and y plus delta y here, minus uy
Right, very good.
2 at y. Great. Okay,
Correct.
so the total sum of all of the forces acting on that little.
This is x1, yeah. So it's not that all the x's becomes y's. X, of course, remains x. But, right, this is y plus delta y.
Object here is just this one plus this one here. So I think we're in a good spot to apply Newton here to look at the total motion of this system here, right? So Newton's
Right, the total forces, total vertical force is just this plus that, okay.
law is going to govern this here. So let's go ahead and write that down. So Newton's second law, right? Which was just mass is, or sorry. Yeah, or let's do this. Mass times acceleration is equal to the sum of all of the forces, right? And if we're looking at this in vertical direction, maybe we can just add little subscript v's here, okay? So, all right, what's an expression for mass? So the mass of this thing is the density here, right? Remember we said that this was units of kilograms per meter squared here, right? Or mass per unit area. So I'm gonna go ahead and take this density here, multiply it by the area of that thing dA. Well, the area of this thing is just delta x times delta y, right? Great, so here's our mass times acceleration in the vertical direction. I think everyone would agree that that's just, here's the deflection in the vertical direction, or the position. So if I take its second derivative with respect to time, I get acceleration. So here we go. Mass times acceleration is equal to...
Amazing. So the definition of acceleration is, right, is relative to time. Very good.
To this garbage down here. So let's write that down here. So it's t times, well, gosh, I don't really want to rewrite it. Tell you what, let's do this. It is this garbage.
Wow, why does the audio go down? Let me hear what it sounds like. Is it really that bad? Relative to time. Very good. The audio sounds good.
To
Doesn't
this garbage
sound
down here. So let's
bad.
write that down here. So it's t times, well, gosh, I don't really want to rewrite it. Tell you what, let's do this. It is this garbage.
But what's
Wow, why does the
interesting?
audio
go down? What's interesting is that I mean, it's very jittery. The video is jittery. I think because I'm downloading this very stream simultaneously. So maybe I'll stop doing that. Okay, back to reality. So again, I'm just trying to derive the 2D wave equation because I was assuming it all along for this discussion, and I don't want to assume. I want to be able to derive everything. Even if I don't derive it myself, I just want to look at a derivation and agree and make sure that I'm following the details. Details are important. Otherwise, I get lost in the shuffle.
Common junk 1 plus junk 2.
Very good.
Okay, just don't want to write this all again here because I want to make it simple. But the left-hand side is just du squared dt squared is equal to this whole other side can basically reduce to tension over density times ux of x plus delta x y1 minus ux
he's moving. So he took this and this thing he's moving over. So rho goes over here and tension comes out. So tension over rho. But what about delta x delta y?
y2 all over delta x here, right? This plus, you get a very similar term, uy x1 y plus delta y minus uy x2y all over delta y. And let's close this square bracket to match that. Okay, all right. I want to look at this term right now. In fact,
How did he do this? So he divided by delta x and delta y. So this is divided by delta x delta y. So all that's left is delta x. And delta x, all that's left is delta y. So it's fine.
let's look at the numerator here. So the numerator here is, what's this first term in the numerator? This is the slope at x plus delta x. So this is effectively slope at the right side of the membrane minus this here is slope at the left side of the membrane. So the entire numerator is basically the difference in slope, or how much did the slope.
Yeah, very, very nice. So this is, if I'm not mistaken, left and right. So the slope in the x direction at this point minus the slope at this point. This is x plus delta x. This is x. y1 is it, and this is y2. Why is this y1 and y2? Why is it y1, y2? Why is this y1 and y2? Did he delete it? Why? Anyway, I think he always explains everything.
Probably go numbers here, right? So we end up with the left-hand side is just du squared y2 all over delta x here, right? This plus, you know, a very similar term, uy y all over here is, what's this first term in the numerator? This is the slope at x plus delta x. So this is effectively slope at the
But it's not the same y.
right side of the membrane minus this here is slope at the left side of the membrane. So the entire numerator is basically the difference in slope, or how much did the slope, the slope of the x with respect to x change. So here's like a rise here, right? Or how much did the slope change? And here's your run as you move over distance delta x here, right? So if you think about this long enough, this is rise over run. It's basically asking how did the slope change as you move from delta x here? Or it's basically saying this is uxx, right?
But y changed. Why did you let y change? Like over here, there's y. There's x1, x2. Why is the x changing? Why is it? Okay, maybe we'll come back to this.
Similarly down here, this term right here, this is slope with respect to y on the back face minus slope with respect to y on the front face. So the numerator of this term is basically how much did the y slope change over a run of delta y. So this here is uyy. So awesome. This whole thing now can be rewritten in a nice compact form here of partial u squared with respect to t squared is equal to t over rho times uxx plus uyy. Right? Let's just call this thing, this is some constant, right? It's just tension over rho. This is like a c squared here. And if you look at this long enough, right? Doesn't this look just like it should be ringing some bells from our vector differential?
I mean, he's just saying it's c squared. Then he's going to say it's 1 over. It should be 1 over v squared, but we will need to prove it.
For calculus discussion, this is just Laplacian of u. So the nice compact format of this is basically partial squared u with respect to t squared is equal to some constant c squared here times the Laplacian of u. And here you are. Here is our 2D wave equation.
I wanted to see that it's 1 over v squared.
Right, and in this case, again, maybe we should fully write this out here. So here, c squared is tension over rho. It's just some number here associated with your problem here. And again, if you look at this long enough, if there's only one spatial dimension, like if there's no y, if this was gone, right, we recover basically our 1D wave equation. So maybe the more efficient route to have this discussion, we should have done this first and then simplified to the 1D wave equation. That's the other way you could have skinned this cat here. So now that we've got the actual, here's our 2D wave equation, let's go ahead and think about solving this thing now in the next lecture. All right. So I think this is a good spot to stop. So if you like the video, please subscribe to the channel. It really helps me continue making these videos. And I hope to see you at the next video when we will solve this for actually 3 independent variables, right? An x, a y, and a time. So I hope to catch you then. Bye.
This is the solution is very, very intricate. The 1D solution took 2 hours. The 2D only takes 1 hour and 13 minutes. It took us like a endless time during the course. But the question is, why is it 1 over v squared? The telegrapher's equation? The heat equation. Yeah, I don't think the speed is important. I don't think we assumed anywhere in this discussion, I don't think we cared about the velocity of the wave. So I don't think it's important right now. So we'll ignore it. So we're fine. Let's continue.
And we write rho of nu equals a times nu squared. The reason this is important is that we would expect each of these modes to act like an energy container, similar to molecules, with an average energy of Boltzmann's constant K times temperature T. Since the number of modes increases as the square of frequency, we should then expect, for a system in thermodynamic equilibrium, the intensity of radiation to increase with temperature and as the square of frequency. That is, much more radiation at higher frequencies. This is the prediction of classical physics.
Okay, so he packed a lot in these two sentences. So each mode should act like an energy container. Okay, yeah, you could say that each eigenvalue, each self vibration is an energy container with an average energy of kT. Why would you say the average energy is kT? How is this related to Boltzmann? I don't know. Again, he's skipping steps. He's just asserting crazy assertions with like no explanation. In thermodynamic equilibrium, we would expect the intensity of radiation to increase with temperature and as the square of frequency. In thermodynamic equilibrium, maybe there's no way out of this, and I just need to read like a quantum mechanics intro book. There's just no way. There's no way out of this. It's just going to be an endless waste of time. In thermodynamic equilibrium, we would expect the intensity of radiation to increase. What is thermodynamic equilibrium? We would expect the intensity of radiation, you mean electromagnetic radiation, to increase with temperature and as the square of frequency. Why as the square of frequency? I mean, we showed in 3D, in thermodynamic equilibrium, we would expect the intensity of radiation to increase with temperature. Why square of frequency? I guess because of this. This is the square of the frequency. Yeah, it makes intuitive sense, but this is not rigorous. This is just intuitive. Rayleigh-Jeans law.
Called the Rayleigh-Jeans law. We write the intensity of radiation as U of nu equals some...
Oh, this is interesting. So the density of frequency, this is the density of frequency?
We write the intensity of radiation as U of nu.
The intensity of radiation? Is the intensity of radiation the same as the density of frequency? Again, he's not deriving, just asserting. I mean, he mentioned KT before, and he mentioned A nu squared before. Now he's multiplying the two. This is the store of energy in the frequency, and this is the frequency density. So together it becomes the intensity of radiation. Like, I don't know. How can you teach like this? How can you learn anything like this? How did Rayleigh-Jeans come up with this equation?
Nu equals some constant A times nu squared times K times T. This is often plotted using logarithmic scales, in which case it forms a straight line. Let's see how this stacks up against observation for the largest box we know of, the universe. Here we have...
Okay, So we need to derive the Rayleigh-Jeans law. Let's go to ChatGPT and ask it to derive. Please derive the Rayleigh. How do you spell Rayleigh-Jeans law? The Rayleigh-Jeans law describes the spectral radiance of black body radiation at low frequencies or long wavelengths, and is an approximation of the more complete Planck's law. It was derived based on classical physics and was later found to break down at high frequencies, leading to what is known as the ultraviolet catastrophe. The Rayleigh-Jeans law can be derived by considering the classical treatment of radiation in a cavity and counting the modes of electromagnetic waves that can exist in that cavity. Here's a step-by-step derivation. Step-by-step derivation of Rayleigh-Jeans law. Cavity radiation, electromagnetic waves. Consider a cubic cavity of volume. Okay, let's see. First, let's look at it like this. Magnitude of wave vector k. Density of states in k space. dn. But what is n? Substituting dn. Energy per mode. Total energy density per unit frequency. Number of modes times the average energy per mode. Spectral radiance. Final form. When did T enter the picture? So in classical physics, each mode of the electromagnetic field can be treated as a harmonic oscillator. Right. According to the equipartition theorem in classical thermodynamics, each mode contributes an average energy of Boltzmann constant times temperature to the system, where Kb is the Boltzmann constant and T is the temperature. Thus, the total energy density per unit frequency, is the number of modes times the average energy per mode. The number of modes times the average energy per mode, which is just, I guess, kBT. kBT is the average energy per mode. So the claim is that each mode on average has the same energy. Why would it have different energy? This is the equipartition theorem is basically argument from symmetry, I think. The spectral radiance. Anyway, that's how we introduced kBT. So kBT is going to stay with us to the end. So kBT is the average energy per mode. And this is just the number of modes. Is it? Okay. I mean, I don't see how you can learn this without being able to derive each step by yourself. I mean, these people spent lifetimes to derive these equations. The least we can do is spend, I would say it would take an hour. to learn this and to get a feel for this. Maybe less, because we already did some of it. The KBT is easy. We've already done that. That makes sense. So all we need, this is so daunting. Let me see if anyone did this. The Rayleigh-Jeans law derivation. Let's go to YouTube. So, oh, come on. Rayleigh-Jeans law derivation. 42 minutes. Rayleigh-Jeans law and the failure of classical physics.
In my last lecture, we discussed black body radiation spectrum. We talked about how we can construct a black body using some kind of a cavity-shaped structure.
Okay, this is 40 minutes. This is 8 minutes.
Try to explain the black body radiation curve with the help of equipartition of energy principle of classical statistics. But unfortunately, Rayleigh-Jeans law failed to explain this curve. In this video of quantum mechanics, we will understand the complete mathematics behind this law and try to find out that at which point this law failed. So let's start the video. Cavity of length A. The length of the cavity, it should be greater than. To explain the black body radiation curve from Rayleigh-Jeans law, consider a large cubic cavity of length A. The length of the cavity, it should be greater than the maximum wavelength of the radiation, so that radiation of all wavelengths will be confined between the walls of the cavity. In the Rayleigh-Jeans law, it has been considered that radiation forms standing wave inside the cavity. The wall of the cavity should be such that it can confine the standing waves of the radiation inside. This requires non-zero conductive walls. If conductivity is zero, then the walls will be transparent to radiation.
What is non-zero conductivity? So it's conductive. What conductive? What I don't even know what they mean, conductive.
Hence, the conductivity of the walls are non-zero, so the electric field at the wall will be zero. This is a boundary condition. Rayleigh-Jeans law.
Non-zero conductivity. So there's no conductivity at the walls. Boundary conditions. Electric field is zero at x equals 0 and x equals a. This is like a Faraday's cage.
Law is based on how many modes of electromagnetic radiation are present in the cavity, and on an average, how much energy is there in the corresponding of each mode.
Okay, so theoretically there should be standing waves inside because that's all that's going to survive. Just standing waves. Nothing else will survive. Everything else will dissipate in time. So it makes sense. So cavity, narrow hole. I think, do they heat it up or do they let something enter from here? I don't know.
So let's first calculate how many modes of radiation are in the cavity. In order to calculate how many modes of the standing wave will be possible in the cavity, first we will consider those standing waves which are present in the x direction.
So it's really straightforward. How many standing waves do you have inside this box? And because of the equipartition, each mode should share an equal part of the energy. What's the question? How much energy is inside the box?
On an average, how much energy, then the walls will be transparent to radiation. Hence, the conductivity of the walls are non-zero, so the electric field at the wall will be zero. This is a boundary condition. Rayleigh-Jeans law is based on how many modes of electromagnetic radiation are present in the cavity, and on an average, how much energy is there in the corresponding of each mode. So let's first calculate how many modes of radiation are in the cavity.
He's saying important stuff. Let's go to normal speed and try that again.
So the many modes of electromagnetic radiation is non-zero, so the reactive walls of has been greater than 0. To explain the black body radiation curve from Rayleigh-Jeans law, consider a large cubic.
He calls him religion. Rayleigh-Jean. Okay.
Cavity of length A. The length of the cavity, it should be greater than.
He calls the cubic box, he calls it a cavity. Okay.
Than the maximum wavelength of the radiation, so that radiation of all wavelength will be confined between the walls of the cavity. In the Rayleigh-Jeans law, it has been considered that radiation form standing wave inside the cavity. The wall of the cavity should be such that it can confine the standing waves of the radiation inside. This requires non-zero conductive walls. If conductivity is 0, then the walls will be transparent to radiation. Hence, the conductivity of the walls are non-zero, so the
it's a Faraday's box.
electric field at the wall will be 0. This is a boundary condition.
So you must use a non-zero conductive material. So you cannot use a cardboard because a cardboard is transparent to radiation.
Rayleigh's law is based on how many modes of electromagnetic radiation are present in the cavity.
How many modes? That's good.
And on an average, how much energy is there in the corresponding of each mode. So let's how much energy is there in the corresponding of each mode. So this is a boundary condition. Rayleigh's law is based on how many modes of electromagnetic radiation
How many modes of electromagnetic radiation
are present in the cavity, and on an average, how much energy is there in the corresponding of each mode.
Okay. So what is the average energy of each mode and how many modes are there? So the number of modes times the average energy per mode is the total energy in the box.
So let's first calculate how many modes of radiation are in the cavity. In order,
theoretically, there should be infinite if we don't limit the frequency to any number. Then you have an infinite, then you have infinity. So obviously you're in trouble.
In order to calculate how many modes of the standing wave will be possible in the cavity, first we will consider those standing waves which are present in the x direction. To be a standing wave between two walls of the cavity, it is necessary to have node points on the both wall. In such a situation, if we assume that the wavelength of the standing wave formed in the x direction is lambda x, then the longest wave possible between the two walls will be lambda x by 2.
Lambda x equals 2a. That's the assumption. That's the maximum. You cannot have more than that. So if lambda x equals 2a, then a equals lambda x over 2. It's fine.
Similarly, the next possible wave will be 2 lambda x by 2 length. In general, the length of the wave.
So the next wavelength is a, which is just 2 by 2. And the next one I don't know.
In x direction will be nx lambda x by 2.
So 2a is lambda, or 2 lambda, or 3 lambda. Yeah, that makes sense.
The same way, the length of the wave corresponding to y and z direction will be ny lambda y by.
Yeah, for symmetrical reasons, y and z should have the same equation. So it's nx lambda x, or nx, or ni lambda I over 2, where I is xyz. N is 1, 2, 3, 4. Yeah. Yeah.
By 2 and nz lambda z by 2. Here, nx, ny, and nz represents the possible number of modes.
Well, I'm following so far. It's pretty good. Good explanation.
In all three directions. These are those waves which are in x, y, and z directions. There will be some more waves in arbitrary directions. Let alpha, beta, and gamma are the angles that wave drawn on the axis x, y, and z respectively. To understand this, let's take an example of wave having modes nx equals to 3 and ny equals to 2. The line joining of the node points of these two waves project the wavelength of the wave in arbitrary direction.
So this is an arbitrary wave direction. I don't know what he's trying to do. A equals that x and y. For example, if nx equals 3, ny equals 2, what is he trying to say?
Let assume the wavelength is lambda, so the projection of the lambda x on the lambda will be lambda x cos alpha. As we know that cos alpha can have the maximum value plus 1, so lambda would be equal or less than lambda x. In the same way, the y and z component of the arbitrary wave would be lambda by cos beta and lambda by cos gamma.
Okay, so lambda x. So you want to have some arbitrary wave lambda, and you have cos alpha beta gamma. So since lambda equals lambda x cos, then if you replace cos, so it's lambda over cos alpha, lambda over cos beta. Fine, everything is correct.
Now, if we put the values of lambda x, lambda y, and lambda z in the equation of number of modes, then we will get the generalized equation of nx, ny, and n.
I mean, okay. It's just that now you have
Let's square.
You're introducing alpha, beta, gamma, and lambda instead of just lambda x, y, z. So nx is 2a over lambda x. So we said a how did we start this? What was the previous slide before this? So this was the previous slide. So we're now at 347. Andrew, I can barely hear you. I don't know why. Why is your audio low?
Wait a second.
Mm-hmm.
Here is
Yeah,
it
it's
cool?
better.
Yeah, that's great.
Mm-hmm.
Have you been talking with Blade or Mario?
Yeah, they were here yesterday. I spoke to them.
Oh, she's crazy. Really?
Mm-hmm.
So can you tell me a feedback about them?
They're very smart, like you.
They are ass. Oh, we shouldn't say that. Wait, you're streaming?
Yeah, I'm streaming.
Oh, my
Why?
bad. Yeah, my bad. Yeah, I would listen to you. I would love that.
That's it. I said they're very smart, like you.
Yeah, that's true. That's true. Yeah.
How do you guys in high school already know so much?
High school? I'm in middle school.
You're not even
You
in
said
high
I'm in.
school? You're still in middle school?
Yeah. Yes.
Oh my god.
But anyway, where are you?
Where am I?
Yeah, I cannot see you.
What do you mean see me? What do you mean? I don't know what you mean by see me.
On your whiteboard. I'm talking about on a whiteboard. But anyway, yeah, I would watch it from the stream. Anyway.
No, I'm not doing
Continue.
whiteboard. I'm doing stream. I'm doing derivation of Rayleigh-Jean equation for black body radiation. I'm doing quantum mechanics.
What is black radiation?
Black
it?
body radiation.
Oh yeah, my bad.
This is
yeah.
how Planck, the derivation of Planck's constant.
Yeah.
So that's
I
it.
understand you.
You what?
Sure. I understand you. That is
Yeah, so
coherent.
it's just the first step of quantum mechanics. I'm trying to get my feet wet in quantum mechanics. I'm trying to understand.
Yeah, super wet. Yes.
Super wet, yeah. Anyway, what do you want to talk about?
Talk about I would have like, let's say 20 minutes to talk.
Okay.
Yeah, 20 minutes. What you want to talk about? Oh, well, Mario is here.
Okay. Here
Sure.
where?
So want to talk about let's say ethics or
Ethics is boring. Ethics is not scientific.
Some of the ethics are scientific.
Namely,
Some, but
let's hear.
super like small amounts. But anyway, would you prefer talking about black holes?
Sure.
Like, wow, yeah. But let's focus about black holes. Like, I would prefer not talking about dark matter and blah blah blah. Yeah, you understand me?
Yeah, I don't
So,
know. I don't know dark matter. I haven't done any research on dark matter.
yeah, sure. So, what do you define as a black hole?
A black hole. You can derive a black hole directly from Newtonian gravity.
Oh, by the way, by the way, you love Catholic Church? Do you love it? I'm not saying believe in it, just love it, like respect it.
I'm sympathetic to all religions. I
Mm-hmm,
have a
mm-hmm.
sympathy, but I told you already, you are religious
Yeah.
because you are poor.
Yes, yes. But you couldn't prove it. But anyway, let's focus about our main subjects. Do you know Galileo? He's a physicist.
Yes,
Do you love
Galileo.
him?
Yes,
He got executed. Sure.
No,
He got
no, he
I have
wasn't.
sent you the I have sent you. He got executed and
No,
trailed by the Catholic Church.
no, he
Here,
wasn't
here.
executed. No,
Yeah, he wasn't executed, but he
no.
went to trail.
He went
He
to
went to trail.
trial, and he was homebound. He couldn't leave his house, but he was not executed because he wrote a letter that he's sorry. He recanted his.
Yeah, but why? Why was he false accused or something? Did he did something which is horrendous, or was that a biased judgment?
I think he was. He didn't like the Pope. There was something personal between him and the Pope, and
Nope.
That's-
Actually, I knew the story.
Okay.
So the story is going like this: the Catholic, it was in the Middle Age. If you're since you're an American native, you know a Dark Age or the West Age. I think you know it.
I think this is before the Black Plague, but this is Italy. I don't know if during those days you could call it the Dark Ages. This is Galileo is the beginning of the Renaissance, I think. The Renaissance,
Yeah.
I don't know. I don't.
Uh,
It doesn't feel
yeah.
like this is the Dark Ages. It doesn't. I don't get.
Actually, the Dark Ages was between 5th and 10th century.
So this
So it
is
was a huge
1500. This is much after the 10th century. This is 500 years after the 10th century. We lost Andrew. But as far as I know, Galileo is 1500 because Newton is 1600. So when did Galileo live? I'm assuming around 1500. Yeah. So Galileo lived from 1564 to 1642. So I think I mean, Newton was born before he died. So when did Newton live? When did Newton live? Newton is like 1600s. 1642. So Newton was, you've hit the free plan limit. Okay. So Newton died, I mean, he was born December and he died January. So there's a year between before Newton was born. Okay. So no more ChatGPT for today. So we need Explore GPTs. There's like more of them. Wix AI website builder, AI PDF, SQL expert, Chat PRD AI for product managers, image generator. Wow, I don't believe it. They're probably not gonna let you generate naked chicks. I'm sure that's the first thing all guys do immediately. And chicks, they probably the first thing they want to see is big peepees. Knowing chicks. Okay, very interesting. Okay. So I'm beginning to become a little bit hungry. So how far are we? We're only halfway through Via Science. Not even halfway. We're probably a third through this lecture. But we really need to finish this to understand, to derive Rayleigh gene. So let me subscribe. When was the last time? 4 years ago. Planck radiation law, a quantum approach. Physica. Very nice. Physica. Very nice. People have beautiful names for their YouTube channels. Okay. Oh, come on. Why am I making so much noise? Let me see. Let me see. I have messages. Let me check a message. Okay, it's too slow. Yeah, I'm fine. No messages. Nothing critical. Okay, so we did this. So we have A is equal. The side of the box is related to these frequencies and these wavelengths, where these are the frequencies, and each frequency has an associated wavelength. No, what is lambda y or lambda x? Is lambda x, is that a constant? Lambda x is some given. We defined lambda x. Lambda x is 2a. That's just lambda x. And then there's all these frequencies based on lambda x, and lambda x is 2a. So you can put here 2a. Anyway. Okay. So this is A. A is this and A is also this. And there's a Z direction. So A. Okay, I don't care about a specific example.
It's on theta by cos beta.
What I care for is this derivation. So we came to the conclusion that lambda equals lambda x cos alpha. Therefore, lambda x equals lambda over cos alpha. Now, so what is this? This is just this inverted. So he says nx. Let's solve for nx. Nx is 2a over lambda x. 2 over lambda x. But lambda x is lambda over cos alpha. So it's 2a cos alpha over lambda. And then you have nx, ny, nz. Okay.
Nz. Let's square all these three equations and sum up. Then nx square plus ny square plus nz square is equals to square of 2a by lambda cos square alpha plus cos square beta.
Why do you add them? Because we want all the modes. All the modes is all the modes of x, all the modes of y, all the modes of z. But why are you squaring them? Squaring and summing the last three equations. No. You're taking three equations. You're allowed to square both sides because you're allowed to do the same to both sides. So you square both sides, square both sides, square both sides. And then you're adding the three equations. You're allowed to add one equation to another equation to another equation. You're allowed to because you're adding the left side to the left side. Since they're equal, you're adding the right side to the right side. That's fine. So you're coming up with nx squared plus ny squared plus nz squared is equal to this squared plus this squared plus this squared. So that's fine. So let me just, I can't see this. Still can't see it. Still can't see it. Why is YouTube so dumb? What am I supposed to do? How can I get rid of this? It's getting in the way. Anyway, so these things are equal to those things. So 2a over lambda comes out squared, and then you have cos alpha plus cos beta plus cos gamma. But this is just 1.
Beta plus cos square gamma. As we know from Pythagorean theorem that cos square alpha plus cos square beta plus cos square gamma equals to 1. So nx square plus ny square plus nz square will be equals to
2a over lambda square, yeah.
Of 2a by lambda. Now if we replace the wavelength with the frequency nu,
this is nu, c over nu, that's fine. You can do that because lambda nu is equal to c, that's fine. So instead of lambda, you have c over nu, that's fine.
Then this will be equals to square of 2a nu.
Right, so lambda is c over nu, sure.
By c. After rearranging this equation, the frequency nu is equals to c upon 2a.
Okay, this is just rearranging to get nu. So nu is, so you're taking the square root of both sides, and then you're multiplying by c, dividing by 2a, and you have nu. So nu is, okay.
Under root nx square plus ny square plus nz square.
Yeah.
Till now, all possible modes was represented by lines in the Cartesian coordinate system. If we consider a coordinate system made up of nx, ny, and nz, then the mode will be represented by the dot. Because each axis of this coordinate system itself represents number of modes in a particular direction. In this coordinate system, if we draw a sphere of the radius rho, then the rho will be equal to the square root of nx square plus ny square plus nz square. Same as r, which is equals to square root of x square plus y square plus z square in the Cartesian coordinate system.
Okay, so we've been through this. Okay. So we've derived nu, which is the frequency.
The dot. Because each axis of this coordinate system itself represents
each axis. All possible standing wave, should be waves, can be represented as a lattice point in the positive octant of the space whose axes are. So this is the positive octant because there's x, y, z. Because this describes a circle. It's just a circle where this is the radius or something, but this is a circle. In the space of nx, ny, and z, nu is a sphere. All possible standing wave can be represented as a lattice point in the positive or yeah, sure.
Number of modes in a particular direction. In this coordinate system, if we draw a sphere of the radius rho, then the rho will be equal to the square root of nx square plus ny square plus nz square.
Yes, I agree. Rho is the radius.
Same as r, which is equals to square root of x square plus y square plus
Yes, it's the same as x squared plus y squared plus z squared equals r. I mean, square root equals r, or r squared, yeah.
z square in the Cartesian coordinate system.
Yeah.
So rho will be equals to 2a nu by c. Therefore, the
So rho equals 2a. So this rho is the radius. Radius equals this, and nu equals that. So you can replace this with rho. So rho equals nu 2a over c. Wow. I'm able to follow. This is a good video. I'm just barely able to follow because he didn't show that your plug what he's plugging in.
frequency nu is equals to 0 by 2a.
I'm wondering if I made a mistake that I didn't ask for a hug and a kiss or a hug. I don't know. Let's continue. This is good. This is a good derivation. So what are we saying now? Well, we're going back to the nu. So nu equals, obviously, nu equals rho c over 2a. Yeah.
Now, to calculate the number of modes, we have to calculate number of mode point of the frequency nu in a specified volume. For that, let's draw another sphere of the radius rho plus d rho. We are willing to find out that
Very good.
volume of the region between both spherical shell. The surface area of the inner sphere will be 4 pi rho square. Now,
Yeah. I just want the surface area. We've been through this. 4 pi rho squared. And this is d rho.
as we have taken only 1 by 8th part of the sphere, so the surface area become 1 by 8 4 pi rho square. Thickness of the region is d rho, so the volume of the shaded region will be 4 pi rho square d rho by 8.
4 pi rho squared over 8, 4 pi rho squared over 8 times d rho is the volume of the orange, I guess, or pink, whatever, pinkish. That's this volume. And he says here that the number of frequencies of standing waves, d nu, is that. That's just this volume. But we're only looking for these dots for eigenvalues.
Therefore, total number of standing wave in this shell will be 4 pi rho square by 8 d rho. As we know that each electromagnetic radiation have the dual polarity, so the total number of mode will be 4 pi rho square by 8 d rho into 2.
What do you mean dual polarity? Due to the polarization of light, you multiply by 2. What do you mean by that? I don't know. I don't know what you mean by that. 39 comments. Okay, this is at 622. 552. Three. No one is asking. 539. Yeah, this is my question. Mm-hmm. Mm-hmm. What do you mean by due to the polarization of light? So there's standing waves, and you're saying that there's two polarizations when it comes to standing waves or something? Okay, 622. I don't think we're going to get an answer, but fine. 622 polarization times 2 or whatever. What polarization are we talking about? I just don't know. Okay.
This denoted by N nu d nu, which
So this is N nu d nu. So N nu d nu equals number of modes having frequency in the range nu to nu plus d nu is the volume of the octant shell between rho and rho plus d rho. Okay.
represents number of modes.
Rho equals 2a nu over c. He's repeating this, and d rho. Oh, this is rho, so d rho as a function of nu is 2a over c d nu.
Of the frequency nu in the frequency range d nu.
I can't see the bottom.
That's number of modes of the frequency nu.
So n nu d nu, I guess, is equal to, we already said, 4 pi rho squared. So this is now rho squared over 8. So this is rho squared. Rho is 2a nu over c. So 2 is 4, a squared nu squared over c squared. Times 2 because of polarization. Times d nu, or sorry, d rho we said is 2a over c d nu. That's fine. Okay, so this is the final form, not the final form, but this is the final form of this page.
In the frequency range d.
So nu d nu, I guess 4 times 4, 64 divided by, 64 times 2 divided by 8, I guess is 8. So 8 pi a cubed nu squared over c squared c cubed. Wow. Wow.
Nu. Now let's find out average energy corresponding to each modes. For that, Rayleigh's law took the help of equipartition of energy principle. This principle simply says that each degree of freedom have the same energy, half kT. If the system has kinetic and potential both energy, then the average energy corresponding to each mode will be kT. The total energy corresponding to the number of modes in the frequency range d nu will be 8 pi a cube nu square kT by c cube into d nu.
Okay. 1 second. So the equipartition of energy principle says that each degree of freedom has equal 1/2 kT amount of energy. each degree of freedom has this amount. It's like a given amount. So this doesn't make any sense. The equipartition, what does it say? Oh my God, this is endless. Okay, we need to take a look at it. Equipartition. I just saw a good lecture about the equipartition. Equipartition theorem. Let's see the equipartition theorem. 14 minutes, 8 minutes.
In this video, I'm going to discuss an ideal gas under.
He's one of the best teachers I've ever seen in my life. He simplifies everything, but he repeats everything multiple times. So this 20 minutes is probably a quarter. Okay, equipartition.
So we're going to do a more formal derivation of the equipartition theorem, which gives us a relationship between the energy and the temperature of systems, where energy is stored in quadratic degrees of freedom. What that means is that the energy is dependent on the square of some variable. So 1/2 mv squared, kinetic energy depends on the square of the velocity, 1/2 kx squared, the spring energy depends on the square of the displacement. So any energy that is stored as a square of some variable, we can use the equipartition theorem for. We're going to write this variable as q. This could be velocity or position or angular velocity, any of those things. Okay, so what we're going to do is we're going to write down the partition function for this energy, these energy states, which is going to be the sum over the states. So we are going to have some distinct values of q, and we're going to sum up the Boltzmann factor for each of those q values. Okay, and now what we're going to do is we're actually going to try to multiply this by some delta q divided.
Okay, he's skipping steps.
So now that you know how to count the number of degrees of freedom of a gas, you're ready to learn about the theorem of equipartition of energy. This is important because it allows us to calculate the internal energy of an ideal gas. So the internal energy is the total energy stored in that gas. What the theorem of equipartition of energy tells us is that each degree of freedom for a molecule contributes 1/2 kBt to the total energy of a system. So Kb here is Boltzmann's constant, which is equal to 1.381 times 10 to the minus 23 joules per Kelvin. So this tells us that the internal energy of an ideal gas is given by internal energy is equal to F/2 times N kBt. So in this equation, F is the number of degrees of freedom, N is the number of molecules making up our gas, Kb is Boltzmann's constant, and T is the temperature measured in Kelvin.
Okay, so 1/2 kBt is some proportion. You multiply it by the number of items and then by the number of degrees of freedom, and that's the total internal energy. Okay, that makes sense. So 1/2 kBt is a proportion that's waiting for us to ask it or to plug in the number of molecules.
Now, if rather than knowing the number of molecules, we know about the number of moles, you can use an alternate form of this equation, which can be written as the internal energy is equal to F/2 nRT.
And then N is the number of moles.
RT, where the lowercase n represents the number of moles and R is the gas constant, which is equal to 8.314 joules per Kelvin per mole. So for example, if we have a gas which is made up of monatomic molecules or single atoms, then we'd say that the internal energy of that gas is given by 3/2 NKBT.
So there's only 3 degrees of freedom.
In this problem, we'll be looking at the equipartition theorem, which is a very useful tool for showing us how molecules can accommodate energy. That is, if we add heat to an atom or molecule, how exactly does it store that heat, and why are some molecules better at storing heat than others? Here, using the equipartition theorem, we'll predict the constant pressure heat capacity, or CP, of carbon dioxide in its gaseous form. Heat capacity tells us how much the temperature of a substance will increase for a given amount of heat added to it, and it can be measured for a system with a constant volume or a constant pressure, as in this problem. So our first step here is to calculate the total number of degrees of freedom for our CO2 molecule. A degree of freedom notes the different motions or ways in which a molecule can move to accommodate heat, and the total number of degrees of freedom in a molecule is given by 3 times the number of atoms in it. Here we're looking at CO2, which has 3 atoms, so 3 times 3 atoms gives us 9 total degrees of freedom. Now that we know it's got 9 degrees of freedom, we can...
Yeah, but could you show us those degrees of freedom?
Equal distribution of energy among degrees of freedom, equipartition.
This is the CO2.
Equal distribution of energy among degrees of freedom, equipartition theorem. In the video on the relationship between pressure and temperature in the context of the kinetic theory of gases, the following formula for calculating the pressure for ideal gases was derived. In this equation, N denotes the number of molecules in a considered gas volume V, for example, the volume of a gas cylinder. Ekin(x) refers to the mean kinetic energy of the molecules. With this kinetic energy, the molecules eventually collide with a boundary surface and thereby exert the pressure P. This pressure can then be experienced as a force acting on the piston. The kinetic energy given in the formula refers only to that velocity component with which the molecules actually collide with the boundary surface. According to the arrangement of the piston and the choice of the coordinate system, the mean kinetic energy therefore refers only to the velocity component in the x direction. Velocity components in the y or z direction, which are directed parallel to the piston surface, do not lead to an impulse on the piston during the collision and are therefore not relevant for the pressure on the piston. Thus, the pressure given in the shown formula refers only to that pressure which is measured in the x direction. However, for the other spatial directions, a pressure can be defined quite analogously, which is linked to the kinetic energies along the respective directions. However, practice shows that the pressure in gases is always equally distributed in all spatial directions, even if only the velocity component of the molecules is changed in the x direction. To show this, the cylinder sealed with a piston can be equipped with 3 pressure gauges. These are mounted at right angles to each other, so that the pressure exerted by the gas in the various spatial directions can be measured separately. In fact, you will find that the pressure for all 3 directions is identical. Now the gas in the cylinder is compressed by pushing the piston into the cylinder. The moving piston then hits the oncoming molecules in the gas with a certain force. On a microscopic level, this process is similar to hitting an oncoming ball with a racket. The moving piston thus increases the speed of the molecules in the negative x. This also increases the mean kinetic energy that is related to force. On a microscopic level, this process is similar to hitting an oncoming ball with a racket. The moving piston thus increases the speed of the molecules in the negative x direction. This also increases the mean kinetic energy that is related to the x direction. Consequently, the compression should only increase the pressure in the x direction and the pressures in the y and z direction should remain unaffected. However, this is not observed in practice. Experience shows that the pressure will increase equally in all spatial directions. According to the given equations, the kinetic energy for all 3 spatial directions must have increased equally. Obviously, the energy supplied during compression must have been distributed equally among all 3 spatial directions. This phenomenon of equal distribution of energy is also called equipartition theorem. So note, the equipartition theorem states that the kinetic energy of the molecules in a gas is equally distributed over all 3 spatial directions and thus the pressure in all spatial directions is identical. The equipartition theorem is a consequence of the random statistical motion of the molecules. These chaotic movements of the particles leads to continuous collision.
No way. Equal distribution of energy among degrees of freedom. Wow. So this is why the pressure is the same in all three directions. That's the equal distribution of energy. Wow.
Collisions in which the molecules subsequently move in different directions. In this way, the originally ordered motions quickly become disordered, with no direction being preferred and thus an equal distribution of speed and energy taking place. The equipartition theorem is not limited to translational motion but applies to all forms of energy at the atomic level, such as rotation and oscillation. In the following we will go into this in more detail. In the video on the relationship between pressure and temperature, it was shown that the mean kinetic energy of a molecule is related to the thermodynamic temperature by the given equation, where Kb denotes the so-called Boltzmann constant. The kinetic energy E is thereby no longer limited to one direction, but to be understood as the total kinetic energy of a molecule. The total energy.
So 3 is because of the 3 directions. You have 3 degrees of freedom, and it's 1/2 kBt. That's the total energy.
Contained in an ideal gas in the form of motion, generally also referred to as internal energy U, is thus obtained by multiplying the mean kinetic energy of a single molecule by the total number of molecules N contained in the gas. We will discuss this equation in more detail.
This is for 1 molecule. This is for N molecules.
In the following. First, however, it should be noted that the 3 spatial directions in which the molecules of an ideal gas can move ultimately represent the possibilities that the gas has to store energy. A molecule can, so to speak, store its energy in the motion in X direction as well as in the motion in Y or Z direction. These possibilities to store energy are also called degrees of freedom. So note. In thermodynamics, degrees of freedom are the number of possibilities to store energy at the atomic level. A molecule of an ideal gas thus has a total of 3 degrees of freedom, that is, for each spatial direction 1 possibility to store energy in the form of a translational motion. For each spatial direction or each degree of freedom F, an energy of 1/2 kBt is assigned for a molecule. The entire gas thus has an internal energy per degree of freedom of 1/2 kBt. These formulas multiplied by the total available degrees of freedom then result in the respective total energy. While monatomic gases only have 3 degrees of freedom in the form of the 3 spatial directions for translational motion, linear molecules such as diatomic.
So monatomic has just 3 degrees of freedom, but if you have 2 atoms, then there's already more degrees of freedom.
Energy. While monatomic gases only have 3 degrees of freedom.
This is monatomic, 1 atom.
In the form of the 3 spatial directions for translational motion, linear molecules such as diatomic molecules can also have rotational motion. In this case, there are theoretically 3 further possibilities for storing energy. These include rotation around the x-axis, the y-axis, and the z-axis. Theoretically, in this
Incredible. So this is already 6 degrees of freedom. So it's 6/2.
case, a total of 6 degrees of freedom result. 3 of translation and 3 of rotation. One will also notice an equal distribution among these possibilities to store energy, regardless of whether it is a translational or rotational motion.
So there's no reason for the energy to be stored. There's no preferred method of storage of energy. This is the equipartition theorem. The universe doesn't have a preference to store energy.
Imagine that the linear molecules in a gas are initially only given a translational motion in one direction, but then sooner or later the molecules will begin to rotate due to the collisions between the molecules. Due to the random motion, the originally purely translational kinetic energy will gradually be converted into rotational energy and distributed equally among all degrees of freedom. For example, the translational kinetic energy in the x direction will then be the same as the rotational energy around the y-axis. We can thus extend the equipartition theorem to arbitrary degrees of freedom. The equipartition theorem states that the total energy is distributed equally among each degree of freedom. Note that the temperature is determined only by the translational kinetic energy of the molecules, regardless of whether the molecules rotate or not. Thus, at a given temperature, the same amount of energy will always be attributed to the translational motion, which is determined by the shown equation.
The translation energy is always the same. There's always 3 degrees of freedom in this universe.
According to the equipartition theorem, however, the same amount of energy must then also be present in the form as rotational energy, as long as the molecules can rotate. Therefore,
this is a diatomic. For diatomic, rotational is 3 degrees of freedom.
For each degree of freedom of a rotational motion, the same formula applies as for the translational motion. This, therefore, also applies to the calculation of the internal energy. A diatomic gas with a total of 6 degrees of freedom thus contains twice the internal energy at the same temperature and the same number of molecules compared to a monatomic gas with only 3 degrees of freedom. Note that for quantum mechanical reasons, not all theoretically possible degrees of freedom can actually be used for storing energy. For example, with molecular hydrogen H2, a very high energy is required for the hydrogen molecule to rotate around the molecular axis. At moderate temperatures, the energy present in the gas is usually not sufficient to cause the molecule to rotate around this axis. The use of this rotational energy is therefore only theoretical. This is then also referred to as a so-called frozen degree of freedom, since this is only actually present at high thermal energies or high temperatures. The hydrogen molecule, like many other diatomic molecules, thus has effectively only 5 degrees of freedom. Note that in many cases, the atoms are assumed to be mass points, including the individual atoms of...
We never said that it has that degree of freedom. We never spoke about that.
Linear molecules. In this case, then no energy can be stored in the rotation around the molecular axis anyway, because effectively no mass is in rotation. In this model, such a diatomic molecule has only 2 degrees of freedom for rotation. That is why in most cases one speaks of only 2 degrees of freedom for rotation and not of 3. The consideration as mass points makes also sense, because otherwise one would have had to take rotational energies into account even for monatomic gases, since spherical atoms can also rotate and thus store energy.
I don't understand. There's 3 directions in which a diatomic can rotate. There's 3 planes of rotation that a diatomic can rotate about, right? This way, and this way. I don't get it.
Moreover,
so why is he saying 5?
This shows that in most cases only 2 degrees of freedom are effectively present for the rotational motion of diatomic molecules anyway. In the case of diatomic molecules, it must be noted that there are generally also binding energies between the atoms, which act similarly to an elastic spring. Due to these elastic bonding forces, the molecule can also oscillate along the molecular axis. One might think that this is only 1 degree of freedom. In fact, however, oscillations contain both potential energies and kinetic energies. Therefore, there are always 2 degrees of freedom for possible types of vibration. In contrast to the actually existing degrees of freedom of vibration, a possibility of how a molecule can oscillate is also called a mode of vibration. Each mode of vibration therefore always contains 2 degrees of freedom. Triatomic linear molecules, for example, can oscillate in 4 different ways and thus show 4 modes of
Why is there 2 ways? I don't know how they're doing their counting. Their accounting.
vibration. This results in a total of 8 degrees of freedom. One vibrational mode results, for example, from the symmetrical stretching of the 2 outer atoms along the molecular axis around the centrally located atom. As another possibility, the molecule can also perform an asymmetric stretching motion by all 3 atoms vibrating along the molecular axis. The third and fourth vibrational mode result from a so-called bending mode, which is also referred to as scissoring. A distinction is made in which plane, vertical or horizontal, the vibrational bending motion takes place. For triatomic
So isn't there one more? This is horizontal, vertical, but there's one more, either horizontal or vertical. There's 3 planes of motion. I don't get it.
linear molecules, there are generally 3 modes of vibration. At the one hand, again, there is a symmetrical stretching of the outer atoms along their molecular axis. As scissoring.
This is so this is so fascinating. It's so mechanical. I miss mechanics so much.
Distinction is made in which plane, vertical or horizontal. The vibration.
When you delve into the quantum world, into modern physics, it's so difficult to get a mechanical perspective. Everyone is trying to get away from the mechanical perspective with all the nonsense. But ultimately, there has to be a mechanical explanation. Oh my God.
Atom. As another possibility, the molecule can also perform an asymmetric stretching motion by all 3 atoms vibrating along the molecular axis. The third and fourth vibrational mode result from a so-called bending mode, which is also referred to as scissoring. A distinction is made in which plane,
Scissoring.
vertical or horizontal, the vibrational bending motion takes place. For triatomic nonlinear molecules, there are generally 3 modes of vibration. At the one hand, again, there is a symmetrical stretching of the outer atoms along their molecular axis. For molecules, there are a distinction is made in which plane, vertical or horizontal.
So this is triatomic. That's like a linear triatomic.
2 degrees of freedom. Triatomic linear molecules, for example,
This is triatomic linear.
can oscillate in 4 different ways and thus show 4 modes of vibration. This results in a total of 8 degrees of freedom. One vibrational mode results, for example, from the symmetrical stretching of the 2 outer atoms along the molecular axis around the centrally located atom. As another possibility, the molecule can also perform an asymmetric stretching motion by all 3 atoms vibrating along the molecular axis. The third and fourth vibrational mode result from a so-called bending mode, which is also referred to as scissoring.
But this can happen along the X, along the Y, along the Z, no? This can happen X, Y, Z. This can happen X, Y, Z, no?
Distinction is made in which plane, vertical or horizontal, the vibrational bending motion takes place.
Okay, so I guess he's agreeing, maybe.
For triatomic nonlinear molecules, there are generally 3 modes of vibration.
This is triatomic nonlinear.
At the one hand, again, there is a symmetric fourth vibrational mode result from a so-called bending mode, which is also referred to as scissoring. A distinction is made in which plane, vertical or horizontal, the vibrational bending motion takes place.
Why only vertical and horizontal? There should be 3 planes of motion.
For triatomic nonlinear molecules, there are generally 3 modes of vibration.
3 modes.
At the one hand, again, there is a symmetrical stretching of the outer atoms along their molecular axis. At the other hand,
Okay, so it's exactly like the linear.
again exists an asymmetrical stretching, where atoms vibrate phase-shifted. The third mode of vibration is again a bending mode, where the outer atoms vibrate in a kind of scissoring motion within the molecular plane, which means that the bond angle oscillates around a resting position. To determine the position of an atom within a molecule, one needs 3 coordinates. 1 x, 1 y, and 1 z coordinate. A molecule within atoms thus needs 3 times n coordinates in total, by which it is then unmistakably defined at a certain point in time. This number of parameters corresponds to the total number of possibilities the molecule has to move, to rotate, and to vibrate. These total possibilities can be divided between the translational degrees of freedom, the rotational degrees of freedom, and the modes of vibration. If the number of degrees of freedom of translation and the number of degrees of freedom of rotation are known, then the number of modes of vibration can be determined with the shown formula. It must be noted that for the internal energy, the actually existing degrees of freedom are relevant, since in these energy can be stored, that is per degree of freedom 1/2 times n times kV times t. For the total degrees of freedom, therefore, the number of modes of vibration must be counted twice, since a mode of vibration contains both potential and kinetic energy. If one divides the degrees of freedom between the translational motion, the rotational motion, and the vibrational motion, then the given equation applies to the total number of degrees of freedom relevant for the internal energy. If the previously derived relationship is used at this point, then the energetic degrees of freedom can also be determined by the number of atoms of a molecule. The table shows the number of degrees of freedom for monatomic, diatomic, and triatomic molecules.
Monatomic, no rotation. No vibration. Total 3. Diatomic. 3 translation. Why only 2 rotation? I don't get it. Anyway. It's a whole universe, apparently. Okay, so this is the equal distribution of energy. This is the equipartition. Let's get back to here, but at this point, I'm really hungry. I'm becoming hungry. Okay, we're going to have to finish this in part 3. Part 3. All right. Let's see the audio.
This garbage down here. So let's write that down here. So it's T times
This and this. Anyway. 1, 2, 3. The whole universe, apparently. No problem. Okay. All right. We're going to stop here. See you later. Bye.